Okay, so today we're going to look at A5 Part 2, focusing a little bit more on how we can write vectors without sketching them, just using numbers. We will do a sketch towards the end, but I think that's going to be helpful because it's a word problem. So anytime you're doing a word problem, visualizing it is usually the way to go. But for simple things, just like adding and subtracting, we shouldn't have to sketch a vector just to do that. There should be an easier way to do it with just numbers, and I'll show you guys what that is. All right, so first thing we're going to look at is what does it mean for two vectors to be equal? So suppose we had two different vectors. Okay, vector v has a horizontal and a vertical component, and so does vector w. Let me draw a picture of those two vectors or an example of what they could be, okay, on the next page. So I go like this. Let's see if I can get a grid. Let's use. Yeah, that's good. All right, so let's say we had a vector here, and it stops there. And then I have a vector over here, and it stops there. Do you think those two vectors are equal?
Yes.
Yeah. They don't start in the same spot, they don't end in the same spot, but that doesn't matter. What makes them equal is the components. How far over did you go? And how far up did you go from the initial to the terminal? If you go over and up the same amount each time, then they're equal, regardless of where you put them. Okay, they're the same thing. So these two vectors are equal as long as these components match and these components match. And in that picture I just drew, they did. I think the horizontal was 3 and the vertical was 1. Yep. So those vectors that I drew were both the vector 3, 1. And if you notice the way I wrote the vector, I used the notation I showed you. I've got these angle brackets, and we do something like this. They're both the vector 3, 1. Now, you can use this as a notation to write a vector, but that's not the notation that is used most often. So what I'm going to do now is show you the final notation, the one that we are going to use most of the time. And that notation is called unit vector notation. And I think this was a question on the homework as well, but can someone remind me, what does it mean for a vector to be a unit vector? Yep, Zach? Its magnitude is 1. So we're going to look at two special unit vectors right now. These two vectors have special names, and these are names that you cannot use. Like normally you can pick any letter you want to name a vector, except for the two letters I'm about to show you. You're never allowed to use these two. So one special unit vector is I. So if you want to name a vector, because you need to in your problem, do not pick the letter I. Pick something besides I. You're not going to use J either, but we'll get to that in a second. So I is defined to be a unit vector, and it points to the right. So if you want to see a picture of what I looks like, it looks just like this, what I just circled. It's 1 unit long, and it points to the right. Right? And there's one other special unit vector we're going to talk about, and that's J. J, again, it's a vector, so it should be bold. J is a unit vector that points up. So I and J are two names you cannot use for vectors because they are special names that mean something else. just to show you a picture, okay, of what J looks like. J looks like that. It's 1 unit long, and it points up. So any questions on what I and J are? So what we're going to do is think of these I and J as like building blocks. We're going to take and we're going to stack I's and J's together to build a vector. And when we do that, I think you'll very easily see what unit vector notation is. All right, so we're going to stack I's and J's together to build a vector right now. Right, so I'm just going to make up a vector. Okay, I think I already have one I made up, and it's the vector 3, 4. So let me draw it. Start at the origin. So there's the vector 3, 4. And we're going to write that vector using unit vector notation. So the way you do it is you start at the initial point and first figure out how many i's we would have to stack together. And our goal is to eventually end up at the terminal point. So the first thing we want to do is move right, and then we'll move up. Does anyone see how many i's you would need to stack together to start moving from the initial to the terminal point? Yep, 3. So we're going to start at the initial point. We're going to do 1, 2, 3. So you have 3 of the I vectors. So if this was a problem that we did yesterday, how would you name this vector? Yep, Chris?
3i.
Yeah, it's just 3i. And when you're writing a vector in unit vector notation, that's the first step. So it's 3i plus we have to put something on the end of it. So we got 3 of the i's. We stack those together. And now how many j's would we need to build up from where we are to the terminal point? Yeah, how many? Yeah? 4. So we need 1, 2, 3, 4. And how would we name that vector in green that we just drew? Yeah?
4j.
4j. And what we just wrote right there, that is unit vector notation. It's basically what we did on Monday with small building blocks. Stack 3 of the i's together, and then plus means put it on the end, put 4 of the j's on the end, and then connect where you start to where you finish, and that would be the vector in black. So 3i plus 4j is the same as this notation right here. Right, so I just wanted to sketch it the first time, but I think you can probably write it without sketching it. It's really just using these 2 numbers, and you put an I after the first one and a J after the second one. You take away the brackets in the column. Any question on how we got that? All right, so that's unit vector notation, and we're going to use this one pretty much the rest of the week. All right, so let's look at some formulas for vectors. Now, these formulas are going to take the place of what we learned on Monday. So we're going to look at how to add, subtract, and scale. All 3 of those things that we did it visually on Monday. If you wanted to add, take a vector like that, take another one like that, line them up, and then you would connect where you started to where you finished. Visual is fine. Okay, we already saw some of the kind of the downsides of it. You need a piece of graph paper. You need something you can draw straight arrows with. So we're going to get away from doing that, and we're going to look at how we can add with just numbers. Okay, no picture at all. So in the example that I'm going to do, I need 2 vectors. And I'm going to define them as v and w. Both v and w have horizontal and vertical components. And alpha, I'm going to use that as a scalar. Anyone remember the three things that can happen when you scale a vector? Or maybe just one thing that can happen when you scale a vector? Yep.
It can change direction.
It can change direction if you multiply by a negative. Yep. What else can happen? Eli?
It can grow.
Yeah, it can get longer. And the third thing that can happen if you scale your vector? Yep.
It can shrink.
Yeah, it can get shorter. So get lengthen, shorten, or flip direction. All right, so if you want to add these two vectors together, you don't have to draw them and then position them and then connect the diagonal. All you have to do to add them is look at the horizontal components, add those together, and then look at the vertical components and add those together. And that would be your answer. When we do it, we're going to practice writing our answer in the new notation I just showed you with I and J, and the old notation without the I and J. We'll try both. Subtraction is the exact same thing. The thing you do have to be careful about with subtraction is the order. Because if you switch the order and you subtract, do you get the same answer? No, you don't get the same answer. So if it's b minus w, then it's x1 minus x2 for your horizontal, and then y1 minus y2 for your vertical. Okay. Questions on the first two? So this one is nice because it takes the place when you do subtraction. Remember, you had to take the second vector, you had to flip it around, and then put it on the end of the first one. That's how you did subtraction. Now we don't have to do that. Just numbers. All right, so this is a scalar. This would be a number, like 2 or 3 or -5. Okay, there would be a number. Scaling a vector is kind of like a distributive property. You multiply your horizontal by the scalar, and then you multiply the vertical by the scalar. It's kind of like distributive property. Now, last thing I don't think we looked at a formula for this one yet, but can someone remind me, what does that symbol mean when you put double bars around a vector? Yep.
It's always positive.
Okay, and so what is it though? I agree that what it is always positive, but what is it? Yep.
You want trying to find the magnitude?
Yeah, the magnitude. And what's a simple word for the magnitude? If you're looking at the arrow, it's what about the arrow? It's the arrow's length. Okay, try to find the length. Well, let's go back to this picture right here. Look at that vector in black. And pretend you wanted to find the length of it. Anybody have a thought how you could get the length of that vector in black? Yeah?
Pythagorean theorem.
Yeah, it's just Pythagorean theorem. Because you know each side. The bottom side is 3, the height is 4, so the black vector would be 5, using Pythagorean theorem. So what did we really do? If we scroll up, we took the horizontal component, and you're going to square it. So probably give you something like that. You take the vertical component, you square it. That'll give you that. And then you add them together, and you take the square root. So horizontal squared plus vertical squared, take the square root. And that's exactly what I have right here. Horizontal component squared, vertical squared, add them up, take the square root. So you're going to see that triangles and trig do come up a lot in vectors. All right. Any question on that last one? All right, so let me give you some actual numbers and try a few examples of each one. All right, so here's two vectors, okay, which I've written in both notations, the new one and the old one. And the first thing I want to do is add those vectors up. Let's do it in unit vector notation first. So that means the I and the j. So v is 2i plus 3j, and w is 3i minus 4j. Okay. If I want to add those vectors together, anyone think they can tell me what the first part would be? The part with the I. Jake?
2 plus 3.
Yep, so can you tell me what you would write if you were adding these together in unit vector notation for the first part?
So you're done with the bracket, right?
We're going to do unit vector notation.
So it would just be, so it would be 2i minus 3i,
And how much is that?
5i.
Yep, so you're going to start with 5i. And then can anybody tell me the next part with the j? Yep.
Minus 1j.
Yeah, minus 1j. 3 plus negative 4. Now, you can do minus 1j, or you could just say minus j. Same thing. Now, what if I wanted you to write that in the notation we learned yesterday? Can someone tell me how this would be written with the brackets? Eli?
5 and negative 1.
Yeah, so 5, negative 1. Either notation is correct. Just look at the problem, read what the directions are and what they want you to write. Questions on that one? All right, so let's try v minus w. So now we're going to subtract. So Matt, when I subtract those, can you tell me what the first part will be?
Negative I.
Yeah, 2i minus 3i is negative I. And Francesca, can you tell me the next part? So what's going to be the next part when we're subtracting them? We have negative I. Well, when we added them, we got negative j, but when you subtract them, you won't get negative j. So can you tell me what numbers are you looking at when you're doing the subtraction?
I'm looking at the
Okay, what number there?
2.
No, the 2, that's part of the I. So anything with an I, Matt already did for us. So we need the part that comes after the I.
So then the 3.
Okay, so 3 is one of them. And what are you subtracting from that?
Would you subtract the negative 4 from that?
You subtract the negative 4.
So then negative 1.
That'd be if you added them, you get negative 1. 3 minus negative 4 is...
Oh, then wait. What? I'm I'm so confused right now.
Oh, yeah, Jack, were you going to say something?
7.
7. So when you subtract the j's, you have 3 minus negative 4.
Would we put the J on the end?
Yeah, you need to put the j on the end, just like that. So negative I plus 7j. And Abigail, if I wanted to write that the old way, how would I write it?
-1, 7.
Yep. -1, 7. So there's an example of subtracting. Let's look at this one, 3v. So for this one, you don't need w. You're scaling a vector, w is not involved in this problem. So Casey, if I take vector v and scale it by 3, what would I get? So what is vector v again? What is vector v? So remember, v is 2i plus 3j. So there's v. And we're scaling that by 3. 6i, yeah. And the second part? 9j. So 6i plus 9j, or you could write it that way as well. Okay. Any question on how we just did a scalar product? Okay, so no sketching, just numbers. And the last one is the magnitude of v. All right, in the magnitude formula, what symbol did I write down? And everything was underneath this. I usually like to write this first so we don't forget it. Yep, square root. So I would put that first so we don't do everything else and then forget that at the end. So you got the square root of, and anyone think they can tell me what's going to go under the square root to find the magnitude of v? So again, you can ignore w, you don't need it. Yep.
It'd be 2i squared plus 3j squared.
Yeah, just the numbers. You don't need the I and the j. So just the 2 squared plus 3 squared. Because remember, when you're finding magnitude, it's a length, and a length has to just be a number. So the horizontal component is 2, vertical component is 3. Think of it kind of like this. 2, 3, find the length of the diagonal. Okay, so you're using Pythagorean theorem. All right, and if we simplify that, what do we get? You don't have to give me a decimal, just simplify what's under the root. Yeah.
Square root of 13.
Square root of 13. Good. Okay, so any questions on finding a magnitude? All right, so just a reminder again, we've said this a couple times already, but if you have a vector that is a length of 1, it's a unit vector. A lot of times what they do to represent a unit vector is they use the letter U. Not saying you can't use the letter U for something else if you want, but like I and J, I'm telling you you cannot use those. But U, you could, but a lot of times U is used to represent a unit vector. So what I want to look at is how can we come up with a formula to turn any vector into a unit vector. So what that would mean is if you have a vector that's too long, how could you shorten it so that it's exactly 1 unit? Or if you have a vector that's too short, How could you lengthen it so it's 1 unit? I want to come up with a formula that describes what to do all of the time, no matter what problem you have. So let's look at a few specific examples, see if you guys see a pattern, and then we'll try to generalize the pattern. So let's say we have length in this column, and then what to scale by to make the length equal 1. All right, so let's say we had a length of 3. Okay, you found the magnitude, your vector is 3 units long. What would you scale that by to force it to shrink to 1 unit long? Yep. 1/3. All right. What if you had a vector that was 7 units long? What would you scale that by to force it to be 1 unit? Yep. 1/7. All right. What if you had a vector that had a length of 1/4? What would you scale by if it was a length of 1/4 to make it 1 unit? Yep, 4. So does anybody see a connection with the number on the left and the number on the right? What's the connection? Eli?
You flip it.
You flip it. So what if you had a vector that was x units long? What would you scale it by? Yep.
1/x.
1/x. So you have to scale the vector by 1 over its length. That's the formula. So let's say you had, I don't know, a vector, let's call this vector v, and this has the horizontal component. This is the vertical component. If you want to force this vector to be a unit vector, you can't change the direction. All you can do is lengthen it or shorten it. But to force it to be a unit vector, find the length. The length would be the magnitude, and scale it by 1 over the length. That's the formula to convert this vector into a unit vector. Scale it by 1 over the length. And that's exactly what you guys came up with right here. 1 divided by the length. Now, if you want to actually do that out using the formula I showed you, you can distribute, it's like a distributive property, and you really end up with this. What really ends up happening is you divide each component by the magnitude. That's what ends up happening when you multiply it out. Right, so if you like words better, it's just easier to understand. We can write it out. So to turn a vector into a unit vector, scale it by 1 over its length. So there's the same thing in words. Scale it by 1 divided by its length. Just don't forget, when you scale it, you have to scale the x and the y. So you have to scale both components. All right, so let's try that using some numbers. find a unit vector for 3i minus 4j. So what do you think the first thing I need to figure out is? Chris?
The length of the vector?
Yeah, I need the length of the vector. Maybe the length already is 1 and I don't have to do anything. But chances are if they're asking you to find a unit vector, it's not 1. Alright, so let's find the magnitude. And Tyler, can you tell me what would go under the square root to find the magnitude of v?
3 squared.
Yep.
Minus 4 squared.
3 squared, and what did you say?
Minus 4 squared.
So when you're finding, think about like Pythagorean theorem. Do we add or subtract in that theorem?
Oh, yeah.
You always add. You can add a negative squared if you want, although the negative is just going to cancel. But you can do that. So 3 squared plus negative 4 squared. And when we do that out, how about Jake, 3 squared is how much? 9. And Sarah, negative 4 squared?
16.
And when you add 9 and 16, you get 25, which means the length of the vector is 5. So my first question, is this a unit vector? Ethan?
No.
No, it's not a unit vector. But what would I scale it by to turn it into a unit vector? Now that I know its length, I should know what to scale it by. Yep.
1/5.
1/5. So it's 5 units long. You scale it by 1/5, it becomes a unit vector. So this is what you need to find. 1/5 v. So Matt, what's going to be my horizontal component when I scale v by 1/5?
That'd be 1 over 15i.
What's the horizontal component now?
3i.
3i, and you're scaling that by 1/5. So what's 1/5 of 3? And think of it as a fraction. No, don't try to do it as a decimal.
So just 1/5.
Well, 1/5 of the number 3. 1/5 of 1 would be 1/5. But what's 1/5 of 3? Is 1/5
Oh,
of
3 over 15.
3.
Oh, 3 over 5.
3/5. So 1/5 of 3 is 3/5. So remember, all you're really doing is dividing each component by your length. So the original length was 3. The new one is 3 over 5. That's the horizontal. So 3/5 I. And what's going to be my vertical component? Yep.
Negative 4/5.
Negative 4/5. Okay. So that's how you turn our vector into a unit vector. You scale it by 1/5, which means to divide each component by 5. And now, if you use Pythagorean theorem on this and you wanted to check it, well, you'd square this. That's 9/25. Square this. That's 16/25. And if you add them up and take the square root, that's 25 over 25. So now that's 1. And you take the square root of it, and it's 1. So this vector is exactly 1 unit long. Okay. So any question on how to scale a vector to make it a unit vector? Yeah?
if it didn't come out to like a nice number like 5, it was like square root of 24, would we have to get it out of the denominator?
So yeah, if it came out like, let's say, I'll just make one up. So let's say you had like 2I plus 3j. Well, the length of that is going to be the square root of 13. That's not a nice number. So when you scale it, if you just divide by the square root of 13, you're going to end up with that in the denominator, and we're not supposed to leave it there. So in this case, the unit vector would be, you could start with doing that. 2 over square root of 13 plus 3 over square root of 13. But then you should fix it so the root's not in the bottom, like this. 2 square root of 13 over 13i plus 3 square root of 13 over 13j. That's how you'd want to write it. Okay, so that's a good question. But any question on what he meant by that? One thing you'll probably never see is a decimal. Unless, for example, you had a vector and you had to divide it by 2. If the length was 2, so you'd scale it by 1/2. Well, you can divide a number by 2 and get a nice decimal. Even if it's an odd number, that's not that bad. But when it comes out to a square root, you won't see decimals. Okay, anything else on that? Yeah?
Would you put that in the quiz or no?
This kind of problem?
Yes.
Yeah, the length, in fact, most of the time the length doesn't come out nice. Because for it to come out nice, it's got to be a very special set of numbers. So random numbers usually come out to a square root. Yeah. 3, 4, 5, that was a special one I picked. Just to make the first one look simple for us. All right, so the last thing we're going to look at is our word problem. Okay, and this is a problem that's about a velocity vector. So, first of all, our problem is going to be 2D. It's going to be a 2-dimensional problem. We're not doing 3. So imagine I had an object traveling like that. Now I know if it was traveling on Earth, it would curve because gravity would pull it back down. But that would complicate things a little bit. So let's pretend like we're in outer space, far away from anything that could have gravitational effect on our object. So we just launch something and it just keeps going. This object is really traveling in 2 directions if you think of it 2D. Can anyone describe to me the 2 ways that this object, or the way that that arrow is pointing? What are the 2 directions? Yeah?
Up and to the right.
Up and to the right. And we can easily find the 2 directions by doing something like this. You can make a triangle out of it. That's what I'm going to do. I just need a straight line. It's not bad, right about there. And by drawing that straight line, it allows me to now make a triangle. And I can clearly see the 2 components. Different color would probably be better. That's the horizontal component of the vector. And that's the vertical. So when you threw, or whatever, you launched this object, you didn't throw it perfectly straight. You didn't throw it perfectly up. You threw it in between. So you threw it at an angle. And it's a combination of that red vector and the green vector that gives you the black vector. Okay, question on that. So what they're going to give you most of the time when you throw an object is, and again, we're not quite here yet, but this is what they're going to give you. What angle was the object thrown at, and how fast was it thrown? Those are the 2 things they'll tell you. And they're going to want you to put that information into a formula to make a vector that looks like this. You're job is to figure out the numbers that go in those two boxes. They're not going to give you those two numbers. They're going to give you an angle, like I threw an object at 20 degrees at a speed of 50 miles an hour. You have to convert it into this. What that basically means doing is finding out the lengths of the sides in a triangle, right? And using that angle to do it, which will be given to you in the problem. So it turns into solving a right triangle, which is something we've done before. All right. So let's, for now, just call this side x and this side y. What trig function could you use that would give you a formula involving this side, and this side? Yep.
Cosine.
Yep. You could use cosine. Anytime you're trying to solve for a horizontal in a vector problem, cosine is usually the trig function you use. And right now, we're trying to do something with the red, which is the horizontal. So, cosine of the angle equals, and what always goes on the other side of a cosine function? Like what goes in the top of the fraction and what goes in the bottom? Just in general, like what's the definition of cosine? Yep.
Adjacent over hypotenuse.
Adjacent over hypotenuse. And when you say adjacent over hypotenuse, what about the adjacent?
The length of the adjacent.
Right, the length. So we need the length of the adjacent, which we're calling x. And the length of my hypotenuse is a vector. What do we call the length of a vector? We have another word for it. It's the what? Yeah.
Magnitude.
The magnitude. So the length of the adjacent is x, and the length of the hypotenuse is that. I mean, I can either do the arrow or I could make the V bold. I need to pick one or the other. I guess I'll do the arrow this time. Now, how would you get x by itself? What would be in this box if I were to solve that? Yeah.
Multiply both sides by the magnitude of v.
Yeah. So it's the magnitude of v times the cosine of your angle. That's what's going to go right there. The magnitude of v is how fast you threw the object. It's the length of the vector in black. The angle, theta, is the angle you threw the object at. Both of those things will be given to you in a problem. Now, we just need to figure out a formula for j. So, we're going to look at it again. This will be given. That will be given. And now we want to find y. So what trig function do you think we would use to get a formula for y? Well, think about what side is y relative to theta. Y is the side that is, yep,
Opposite.
y is opposite. And what about v? What side is that in triangle? Yep,
Hypotenuse.
hypotenuse. There's only one trig function that has those two in it. Which trig function would it be? Jack?
Sine.
Yep, it would be sine. So let's set this one up. Sine is the length of the opposite over the length of the hypotenuse. Well, the length of the opposite we call y, And the length of the hypotenuse is not v, it's the magnitude of v. All right. And you do the same thing again to get y by itself. Y equals the magnitude of v sine theta. There's your formula for y. So now, fill that in right there. Once you fill in those two things, that is the formula for a velocity vector. All right, so it's going to be magnitude of v times the cosine of theta and whatever that comes out to, that goes in front of I, plus, now you need your vertical. That's magnitude of v sine theta. And whatever that comes out to goes in front of the j. So there is your formula for a velocity vector. It's really just finding two sides of a triangle. Again, this is the initial speed. Remember, magnitude represents how fast something's going, so it's the speed. And this is the angle the object is thrown at. And it's the same thing over here. All right, so let's try the example I have, the last one, okay, on the next page. We just have to fill in our speed and our angle into that formula and see what we get. Okay, any questions on the formula? All right, well, here's our example. It says we're throwing an object at 50 miles an hour at an angle of 30 degrees. Find the velocity vector and write your answer in unit vector form. Unit vector form means with an I and a J. The only other form that you guys know is the one that has the brackets. All right. So, using the formula that I just showed you and those two numbers, can somebody tell me what the calculation is in front of the I? Eli?
50 cosine 30.
50 cosine 30. That's what goes in front of the I. And can somebody else tell me what's going to go in front of the J? Chris?
50 sine 30.
50 sine 30. Okay, and try to remember what you're really doing here. You're throwing an object at a 30-degree angle. There's the ground. The object is being thrown at a 30-degree angle. The speed of the object is 50 miles an hour, which means the length of this side in red is 50. What you're finding are these two sides. 1, 2. That's what those two calculations are going to do. So now we just type it in. 50 cosine 30. Make sure you are in degrees, because this problem is in degrees, so I need to switch the mode. 50 cosine 30. That gives me 43.3 I. And then 50 sine 30 gives me 25j. So if I got 25j for the last part, what does that mean the sine of 30 must have been? Yeah.
1/2.
1/2. Yeah, that's a special one. Sines and cosines of 30s come out to numbers we've done on the unit circle, and 1/2 is one that comes up a lot. So the sine of 30 is 1/2, and 1/2 of 50 is how I got the 25. So there is a velocity vector that represents this work level. This 43.3, what component of the vector is that? That's my Chris?
Horizontal.
Horizontal, and the 25 is my
Vertical.
vertical, and these are really speeds. So what this means is if you were standing in front of me and you threw this at me, it would be coming at me at 43.3 miles an hour. You say, well, why not 50? I threw it at 50. Yeah, but you didn't throw it straight at me at 50. You threw it at an angle. Like if you threw it straight up, it wouldn't come at me at all. Even if you threw it up at 50 miles an hour, the speed towards me would be 0 because you didn't throw it at me. So some of your energy went into throwing it up. So it's coming at me at 43.3 miles an hour, and its initial vertical speed is 25 miles per hour. I say initial because the second you throw an object and it leaves your hand, it's slowing down the whole time until it hits its highest point, and then it comes back down. This speed minus wind resistance never changes. If you throw something horizontally, it never slows down unless there's wind resistance. But gravity slows it down vertically. Okay. Questions on that? All right, so that's the second part on vectors. So tomorrow we'll do the third part, which looks at how we can take two vectors and multiply them. And then tomorrow night, for homework, we will have the take-home. Okay, the take-home will cover the first 3 sections that we do. And then Friday, we're going to do the 4th section in class. Any question about the take-home or plans for the week on that? So the take-home would be due the next day, probably earlier in the morning, so that way I can have your grade for you by the time you come to class on Friday. That's the plan. All right, so homework. Remember, it is in a different book, but the PDF that I uploaded, that's the correct PDF, so just use that. 25 to 47 odd, and 55 and 57.